All right, so let's get started here. Today we're going to be starting a new chapter. We're actually going to skip ahead a little bit to chapter 26 on transition metals, and then we'll come back to chapter 20 after this, or 19 maybe. All right, so this chapter is going to revolve around transition metals. Hopefully we remember from first semester, where do the transition metals live on our periodic table? The middle. Right in the middle, absolutely. It's called the D block. But yes, in the very middle are our transition metals. Okay? And what we're going to see with our transition metals, for example, if we have an iron ion, iron 3, is that these are going to react with these compounds to form what are called transition metal complexes. Okay, so again, these are what are called transition metal complexes, or more often just a complex. What makes these kind of weird is that we have these what are called these cyanide ions bound to our metal ion. Okay? But these are what are called, they're not covalent bonds, they're not ionic bonds, they're what are called coordination bonds. All right, so these transition metals, they form complexes. These complexes, you have these, in this case, it's these cyanide ions bound to these iron ions. But these bonds are these special type of bonds called coordination bonds. All right, a coordination bond is similar to a covalent bond in that electrons are being shared, but they're not as strong. They're almost like halfway between an ionic bond and a covalent bond. Okay, they got their own special name when we're talking about transition metals, when we're talking about these transition metal complexes. Again, these are what are called coordination bonds. What's up?
What's the difference between a coordination bond and a polar covalent bond?
So polar covalent is that those electrons are being shared between those two atoms. Coordination bonds are similar in that you're sharing electrons, but it's not as strong of a bond. And really the real difference boils down to like a quantum mechanical calculation, which is a little above our pay grade here, all right? So for our purposes, what we really need to know is our transition metals form these complexes, and the bonds in those complexes are what are called coordination bonds. All right, some other vocab that we're going to learn here is that the metal ion in this reaction is what's called a Lewis acid. All right, and the other thing, so this is our transition metal. The other thing in our reaction is what's called a ligand. And our ligand is playing the role of a Lewis base. I absolutely hate these terms because they have nothing to do with acids and bases that we just learned about. They're their kind of own special little category. A Lewis base donates electrons to a Lewis acid. All right, so they kind of get their name from that sort of idea that the Lewis base is donating electrons, the Lewis acid is accepting electrons. All right, but again, nothing to do with acids and bases.
So is it the reverse of like a normal acid and base since the base is donating?
Yeah, yes and no. So a normal base also has this pair of electrons that's reaching out to grab that proton. But yes, the donating and accepting is switching, okay? But bases do have electrons that accept that proton, so yeah. Bottom line is, look, for me, having studied chemistry for a while, Lewis acids and bases sit in a completely different place in my brain than acids and bases, than Bronsted-Lowry acids and bases, right? We sort of completely split them up. I know they got that same word, acid and base, in there, which makes it a huge pain in the butt, but I put them in two different categories, okay? These reactions with our transition metals will involve the Lewis acids and bases, right? We have pairs of electrons that are being donated. All right, and then the other thing that we want to note about these complex formations is that these equilibrium constants are humongous, right? The KEQ governing this particular reaction is on the order of 10 to the 35. All right, and a big number like that, what does that favor? The products or reactants? And let me just say, I heard some debate out there. I can't remember which one it is. It's not really a memorization game. What's the one thing we have to remember about our equilibrium product? What's the one thing, our equilibrium expression? What's the one thing that we chant to ourselves when we build an equilibrium expression? Products. Well, that was a terrible bracket. Products over reactants. So if this number right here is really big, that means that products, the top number has to be big and the bottom number has to be small, right? So that's a reaction that favors the products because you have that really large KEQ value. All right, so these tend to be very favorable reactions that go basically 100% to completion because they have these extra huge KEQ values, right? Very favorable formation values. All right, and we're going to talk a lot about these complexes here. By the end of it, we're going to be able to look at a complex formula like this and determine the electron structure in that. And we're going to learn what's called crystal field splitting, where we learn about colors of these complexes, all that crap. But the first thing we got to do is kind of rewind in our brain and review some stuff from the first semester here, okay? Specifically around electron configurations. All right, so again, we're going to be focusing on this portion of our periodic table, our transition metals. All right, and then somebody accurately referred to this not just as the transition metals, but as the D block. All right, what we need to be able to do is something that we learned how to do last semester, and that is to take a compound like, for example, chromium, and determine its electron configuration, the 1s2, 2s2, 2p2, or 2p6, all that business, right? So let's just review how we do that again. Again, the middle portion here is called the D block. Over here, this is the S block. And then all the way on the other side, this one over here, the P block. And then this one down here, which we really don't have to worry about because we're not going to be dealing with anything big and huge like that. This is the F. Well, I'll make you a deal. We don't have to deal with the F block. All right. So the other thing, once we split our periodic table up into these portions, we got to then be able to number. So the S block, we start numbering our rows starting at 1. So this first row here is the 1s row. The second is the 2s, 3s, 4s, 5s, 6s. Right? Those correspond to the rows. We're going to do the same thing for our P block. Let me clean this up a little bit. God damn it. All right. But in contrast to our S block, for our P block, we don't start numbering at 1. We start at 2. So this is the 2p row, the 3p row, 4p, 5p, 6p. Okay? Notice that I've conveniently excluded helium from this P block. Helium's kind of an oddball. It's very inert. It's got a full valence shell, so we put it with the noble gases. But really, it's got a 2s configuration, so it kind of lives over here. Or I can kind of think about it as being over there when we do our electron configuration. All right, and then lastly, we got to number our D block here. Right, my S block, I started at 1. My P block, I started at 2. For the D block, what do we think we're going to start at? 3. So this is the 3D row, 4D, 5D. All right, now, the easiest thing to do, I think, is to build your electron configurations backwards, right? So we're going to start at the last orbital that gets filled in. Chromium lives in the 3D row, right? So its last orbital is going to be the 3D, and it lives in position 1, 2, 3, 4 in that D block, so it's 3D4. Right? That's the last orbital in that electron configuration. Okay? But now I got to include everything that comes before it. Right? So in front of my 3D block is my 4s row. So I got to include that. A full 4s, 4s2. What's in front of 4s? Now I got to go back, right? So it's like you're reading and you're reading backwards. Now I'm going to go back to the next line, this line here, 3p. So 3p6. What's in front of the 3p? The 3s. So 3s2. What's in front of the 3s? That's the 2p. In front of that is the 2s, and I didn't leave myself enough room because then in front of that is the 1s. What's up?
Chromium, one of those ones where you have to.
Yeah, maybe. We're not gonna worry about that. All right, let's just deal with it like we're gonna pretend like there aren't those weird exceptions here. I think you're right though. I think I picked a bad example. 4S1 3D5, yeah, whatever. We're gonna save that for the first semester. Right now, as long as we can read it, we'll be good. All right. Can you start at argon and? Oh, the abbreviation? Yeah, we'll do that here in a second. All right. We need to be able to do both. Okay. So these are what are called the full electron configurations. So just to practice that, everybody take a second and now give me the full electron configuration of, let's do iron. All important iron on our periodic table.
Okay, yeah, like.
You don't like reading. You're there. Really?
All right, so iron lives in position 1, 2, 3, 4, 5, 6 in that 3D row. So 3D6, and then everything else that comes before it. All right. And then, yes, absolutely, as was mentioned, if here's my electron configuration for iron, 1s2, okay, if I were to do the electron configuration for argon, based on where it lives on the periodic table, I would get 1s2, 2s2, 2p6, 2p6, 3s2, 3p6, and notice how this, in my electron configuration for iron, is the same as my electron configuration for argon, so we can abbreviate our electron configuration using this noble gas abbreviation. Okay, and what this bracket means is insert argon's electron configuration. right? So bracket argon means the electron configuration for argon. And then if we want it for iron, we got to add that 4s2 3d6 to the end there. So this is what we call the full electron configuration. And this is what we call the noble gas abbreviation. All right, so for the sake of practice here, one more. Y'all give me the, we'll do the noble gas abbreviation for niobium. What's up? That's what we're, yeah, that's what you're doing. Yep. And for niobium, which noble gas am I going to use? Krypton. And then I got to include that extra stuff that makes it niobium. That's the 5s2. And finally, the 4d3. All right, so in an ideal world, this is all just like common sense review you got down. This is going to be a really important step in terms of understanding these transition metal complexes. So we need to be able to draw the electron configurations. And not only for the transition metals, but also their ions. All right, so iron has a lot of different ions that it forms. One of which is the iron 2 ion. That's a nice stable iron ion. We said that the electron configuration for iron we had here. All right, so when a transition metal becomes an ion, first of all, do transition metals become cations or anions? Cations, because cations are positive. Cation, cat, pause, all right? All right, so cations are positive. So when a transition metal becomes a cation, does it gain or lose electrons to get that positive charge? It's going to lose those negatively charged electrons, right? So I have my iron electron configuration here. And now I want to figure out what it is for the iron 2 ion. And you're telling me that it loses electrons to become that cation, right? So what I'm going to do is I'm going to pull electrons from this configuration here. All right? These all represent electrons in iron. If I'm going to decrease my number of electrons, I got to remove them from this configuration here. Okay? Importantly, how many electrons am I going to pull out of this configuration? 2, because of the charge, right? Importantly, we're going to remove electrons from the outermost s orbital first. Okay? So even though this 3D is the last one listed in my electron configuration, when I start pulling electrons out, I'm going to remove it from this 4s orbital first. Okay? So since I'm only removing 2 electrons, both of them are going to come from that 4s orbital. So my electron configuration for iron 2 would be the same all the way up until the end there, where now I don't have any more 4s electrons. I only have my 3d6. Right? So again, we're going to pull electrons from this configuration. We're going to remove from that outermost s orbital first. Any remaining electrons to be removed will come from the outermost d orbital. All right, so we pull from that last s orbital first. If we need to take any more away, we'll take it from that last d orbital. All right, in the case of iron 2, we were done when we got rid of those 2 s. Everybody take a second then, based on what we just discussed, and tell me what the electron configuration would be for the iron 3 ion. All right, so I'm going to take electrons away to form iron 3. How many do I need to take away? 3. So the first 2 are going to come from where? The 4s. And then I still got 1 more I have to take away, right? That only gets rid of 2. Where's that last one going to come from? The 3d. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Cool, so we get our electron configuration for our metal, and then we're going to start pulling electrons away to make these ions. Again, we're first going to remove from that last s orbital. Anything that we still got to take away, we'll take away from that last d orbital. What's up?
How come it's 35? Not like entirely.
Because there was only one more electron that I had to take away to get to a +3 charge. To get to a +3 charge, you had to take away 3 electrons. 2 of them came from here. 1 of them will come from here. If I made it 3d0, all of a sudden I've gotten rid of 8 electrons, right? I'm not trying to get rid of that many.
Oh, so you're taking like one by one. I mean, it just requires.
I'm taking 3 of them total.
Yeah.
All right, so given what we did before with niobium, everybody tell me what the niobium 4 ions electron configuration would be. You can keep it in that noble gas abbreviation if you want. All right, so how many electrons am I going to take away? 4 total. Where's the first one's going to come from? The 5s, so that'll take out all 2 of those. And then I got 2 more left over, and they're going to come from the 4d. So this would leave me with just 1 4d electron. All right, so more terminology here. The charge on the transition metal ion, we call this the oxidation number. In the first semester, you might have learned this whole logic for determining the oxidation number of all elements. When we're talking about transition metals, because they form cations, we're specifically referring to the charge on that transition metal. All right, so it gets its name because what's called an oxidation agent accepts electrons in a reaction. Okay. So then the higher the oxidation number, the larger that positive charge is. What do we think? Do you think it's going to be better or worse at accepting electrons if it's got a large positive charge? Better, right? So higher oxidation number implies it's better at accepting electrons. All right, that name oxidation sounds a lot like what element? Oxygen, and that's because a lot of the history of studying these reactions involved oxygen. It was kind of a concept that was expanded, but that's why it's got that kind of oxygen name built in there, all right? But we kind of want to divorce it from the element oxygen. It's really the charge on our transition metal ion. All right, so rust is Fe2O3. All right, that's the formula for rust. All right, and you guys can just trust me on that. What you need to be able to do is determine the oxidation number of iron in rust, in this compound here. All right, and what we got to do, so transition metals, they can really, given a transition metal, you don't know just by looking at the periodic table what the charge, what the oxidation number is going to be. Transition metals can form several different ions. All right, so we always got to go based on what we know, which is the anion. Let's get rid of all this business here. And let's remember, for these simple monatomic ions, single atom ions, we can determine their charge just by looking at the periodic table. My noble gases, what type of ions do they like to form? Awesome. Trick question, right? They don't like to form ions. They got complete octets. They're perfectly happy. They're not going to give electrons. They're not going to accept electrons. They're cool as is. They don't want nothing to do with you, right? But my halogens, the next column over, what are the charge on my halogen ions? -1. And then we just go from there. What about the next column over? -2. And the next column over? -3. So given a formula like Fe2O3, what we know is the oxide ion's charge, because based on where it lives on the periodic table, what's the charge? -2. And we got 3 of them, right? So if I sum it all up, what's the total amount of negative charge I have here? -6. Okay. There's going to be this important rule that we're going to use over and over again, which is the sum of the oxidation states in a compound equals its net charge. Fe2O3, what's the net charge? 0, right? If there was a net charge, it'd be written up here in that top right corner. But there's no charge written there, so I know that it's neutral. So my oxidation states have to sum to 0. So then how much positive charge do I have in this compound? +6, right? Because it's got to sum up to 0. I got these 2 iron ions. If they both add up to +6, what's the oxidation state on each of them? +3. Okay, so this is the same process you would have had to go through to name this compound. Rust is more formally referred to as iron 3 oxide. And again, that 3 is the oxidation number on the iron. Because I know my sum of my oxidation states has to equal 0. Since I have 3 oxygens with a -2 charge, that means that's -6. The only way that's going to sum to 0 is if the total amount of positive charge is +6, and I have 2 iron ions that are going to add up to +6. All right, so let's do one more. A cobalt chloride complex here, COCl4 with a -2 charge. Everybody take a second and tell me what the oxidation number is of cobalt. All right, so I have, again, the cobalt could be anything. I got to figure that out from the formula. But what I do know is the chloride, right? What's the charge on that chloride? -1. And I got 4 of them. So they're all going to add up to a total amount of negative charge of -4. And the sum of my oxidation states have to equal the net charge on that molecule. So everything's going to sum up to what? -2. That's my net charge. So what? -4 gives you -2. +2. And I only have 1 cobalt in this formula, so what's got to be the charge on that cobalt ion, or the oxidation state, the oxidation number? +2. All right, so then to sort of like wrap up everything that we would have learned today, what can I ask you to do? I could say something like, what is the electron configuration of manganese in this complex here? Rolling it all together here. All right, so first you'll have to figure out what the oxidation number of manganese is, and then you can build its electron configuration. Once you know that charge, once you know how many electrons to remove. All right, so we're trying to do the manganese, but we got to figure out what that charge is first. So what's the charge on the manganese, what we call the oxidation number in this complex? right, so again, step one, we got to figure out the charge here. I have two sulfide ions, each have a charge of -2. How do we know that? Based on where sulfur lives on the periodic table. Oops. And if I sum them up, I got a total amount of negative charge of -4. My oxidation states will have to add up to what? -1. So what? -4 gives you -1. 3. So my manganese ion has a oxidation number of +3. Manganese has an electron configuration of argon 4s2, 1, 2, 3, 4, 5, 3d5. If I'm going to form a manganese 3 ion, I'm going to remove how many electrons? 3. I'm going to first pull from the 4s. That'll get rid of all those. And then I got one more to take away from the 3d orbital. So 3d4, argon plus 3d4.